Hi, I'm Mrs. Burns, and welcome to Lecture 4 of our Chapter 7 unit on nuclear reactions. In fact, this is the last lesson of Chapter 7. So let's review some things that we've already learned in our chemistry unit. We already know that chemical reactions occur, and that is when the reactants simply rearrange themselves to create products. And we saw that the mass remains unchanged in our conservation of mass lab. And we also know that the protons determine what that element is. So as long as there's a certain set of protons, we can look on the periodic table and find out what that element is. And in chemical reactions, the nucleus doesn't change. Now today, we are going to start talking about nuclear reactions, which are different from chemical reactions. So in this case, the atoms do change. They are not just rearranged like in chemical reactions. So all subatomic particles are involved this time, not just the electrons. So we're not just talking about the electrons in the outer shell. Today we're going to start talking about the protons and the neutrons as well. And finally, energy should be our keyword of the day because we're going to talk about it over and over. Tons of energy is required and tons of energy is released for nuclear reactions. These occur when an atom's nucleus changes by either gaining or releasing particles or by gaining or releasing energy. We'll talk about two kinds. One is fission, and that is a reaction that splits a nucleus, and fusion combines elements. So we use nuclear reactions every day all around us for nuclear technology, to generate power, and also for even medical treatments. For example, you can inject radioactive dye into somebody and then take an x-ray and see that in the x-ray. So let's talk here specifically about fission. The idea behind nuclear fission comes from something you already know, and that is that like charges repel each other. So if you think of a magnet, two sides of a magnet don't want to go together. So this can occur naturally, or we can push like charges together forcibly. So many charged protons in a nucleus will repel each other, thus creating an unstable nucleus. So let's just draw one here that has 1, 2, 3, 4, 5, 6, 7, 8 protons in this nucleus. We're not going to draw the neutrons, just the protons. So all of those particles, they're all going to want to get away from each other because positive doesn't like to be beside positive. So the nucleus will then split. And this will form smaller and lighter elements as well as releasing lots of energy. So let's draw what this would look like. This guy's going to split apart to maybe 1, 2, 3, 4, 1, 2, 3, 4 into these different smaller and lighter elements because protons are pretty heavy. Plus energy. I'm just going to do an E for energy today, and you know what I mean. It's like that kabow energy. So we can see this naturally in alpha, beta, and gamma decay. And we have little symbols for these, alpha, beta, and gamma. So we can use fission for a couple of big things. One is electricity. And we see this in nuclear power plants, for example. We have these power plants with all this steam coming out of them. The steam is basically a product of all that energy forming, and the steam drives the turbines that we can use then to connect to electrical generators. So we've got the steam producing, the energy producing, all this good stuff from nuclear reactions, so we don't need to use fossil fuels. However, the products of these nuclear reactions are radioactive, so we do need to store them, and that can be a problem. Also, you can use fission for weapons. You may have heard of nuclear weaponry or nuclear warfare. There is a lot of worry about nuclear bombs being used in future wars, and that can lead to big, like those mushroom clouds, and when that goes into the air, that can cause changes to our environment even. For example, ice crystals forming at the top of that cloud and then getting giant 100-pound hailstones coming down. So that can be a big worry as well. We can also, however, force fission to occur. So if this here was natural, this guy splitting up and creating energy, we can also force it to occur. And this can be accomplished by projecting or shooting these alpha, beta particles or gamma rays into a nucleus. So we're actually shoving them in there. This requires energy to do that because these are positive and we're shooting them into a positive nucleus. So we're going to use energy. So let's look at an example. How would we write it? Force a helium atom into a nitrogen atom. Well, we know that helium looks like, oops, this should be 2. Helium looks like this. And we are going to add that to a nitrogen atom, and we know that symbol is here, nitrogen. So when we do that, we are going to create oxygen plus a hydrogen atom. So as this occurs, we are now shoving that helium atom into the nucleus of the nitrogen. Now we've created oxygen as well as a proton or helium. So here this helium, this can also be written as the alpha, that's another way of saying it, or this hydrogen can also be written as a proton. That's another way of saying it. So notice here that the alpha particle is in the reactant category. When in alpha decay, the alpha ends up in the product category. So please take note of that when you see alpha or the helium or even the beta or the electron in, or even a neutron in the reactant category, that we're talking about nuclear reactions. So like I mentioned, the the positive, getting all ahead of myself, the positive alpha particle is naturally repelled by those protons in the nitrogen nucleus, so we're really going to have to shove them together because they don't naturally want to go together. Also, please note that we have 14, 15, 16, 17, 18 as our mass on the reactants and 18 as our mass on the products. We have 9 as our atomic number in the reactants and 9 as the atomic number in the products. So we are balancing these reactions as well. Let's look at a case study a little bit deeper into uranium. In this case, we're going to inject a neutron. So not an alpha particle. A neutron symbol would be like this, and it's blasted into a uranium-235 nucleus, which fuses and becomes temporarily uranium-236. But it doesn't last long because it's super unstable. So it will then quickly break down into krypton-92 and barium-121, as well as 3 neutrons and a whole lot of, you probably guessed it, energy. So let's write this out. How would it look in an equation? You have a neutron getting blasted in to uranium here, and that becomes temporarily uranium-236, which breaks up into 2 smaller elements, krypton-92 and barium-121, plus 3 neutrons, 1, 2, 3, plus energy. So you might notice here that we've just created more neutrons at the end. We started out by blasting a neutron in, and now we're creating more neutrons and energy. And we actually use this reaction in the Canadian power plants because it creates so much energy. So the neutrons that are produced can be used again and again to drive more reactions. So you take, say, this guy, and you add that to a different uranium-235, and you take this and you add it to a different uranium-235, and they're going to start adding on and making more reactions, and then you've just made 3 more neutrons, which go find their own uranium-235s. So this can quickly create huge amounts of energy, and we call this a chain reaction. Now this can be bad because, well, if this incurs more and more and more and more energy, you could eventually have a huge nuclear explosion. And because we're not all evil scientists and we don't all want to blow up everything, we want to control these reactions. So we can use materials that absorb those neutrons that you're producing. So in Canada, we have something called CANDU, Canadian Deuterium Uranium Reactors. And so we use deuterium as an isotope of hydrogen. And why are we talking about this? Well, it has 1 proton and 1 neutron, making it twice as heavy. And this hydrogen can then be used. Remember that water is made up of H2O. So this hydrogen is used to make this heavy water. And this heavy water is used to control these reactions that are being created with all these extra neutrons. So this heavy water can help moderate things. Also, there are things called control rods that can also be used. Now, the problem is that these control rods and this heavy water does hold on to that radioactivity for a little while. So how do we store that radioactive waste? What do you do to dispose of it? The daughter isotopes are also radioactive. And it does take time for this to not be radioactive anymore. So we're going to talk in class about viable ways for energy production. Last but not least, nuclear fusion. Now this part's short because we already know the whole idea, and this time we're just going backwards. So this is essentially the opposite of fission. So we've got here an example where these two elements are coming together to make blammo, one big unstable element that then breaks up into other particles. So let's look at an example. A good one found in your textbook uses hydrogen and another hydrogen, but these are special hydrogens. These are a couple isotopes. So these are different isotopes of hydrogen. And if you stick those together, you're going to have to force them together, and it uses quite a bit of energy. Then you're going to get helium, or an alpha particle, you can write either one, plus a neutron, plus energy. And you can use that energy for making whatever you want to make. Now, there is a problem with fusion, and that is that in order to cause this to occur, the environment has to be super high temperature as well as super high pressure. And it's pretty difficult to find a container or a vessel that will hold these elements at such high temperatures without the vessel itself becoming destroyed. So this is pretty difficult to do. Now, this is really just a summary. There's so much good meat in your textbook. I really would like you to read it, please. And it's section 7.3 of your book. There's a super good comparison chart, page 321. Please have a read of that and make sure you really understand the differences of fission and fusion, and that you understand how they're occurring, and that you can also write out these reactions. We're going to practice this more in class over the next couple of days.